Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And that's this video here right now. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
All right, so I think most people have this typed up. If not, we'll be kind of back and forth in this code file, so you should have some time to see what you missed there. So the idea here that we're going to go through is a little bit of anti-debugging techniques. And like I said before, I wanted to actually write out a couple of these so we can see them, how they're implemented, and then maybe think about how we could defeat them if we were the analyst as well. So simple C program here. In the main function, we're just going to say, hello, ask the user, are you debugging me? We'll implement all of our checks below that. If one of those checks figures out that there's someone debugging the program, we're going to exit with a status of -1 just to show the program closed kind of unexpectedly. And then at the bottom here, if they make through all the checks, we're going to have them enter a number. That serves no purpose other than to keep the console application open. So since it's like a command prompt, like CLI application, it'll close right away once it's done executing, so we won't be able to see if we actually made it to the bottom or not. So just a kind of a cheating way to pause the program at the end. So on the Windows side of things, there's a few different techniques that we can use for anti-debugging. And really the purpose of anti-debugging is if somebody captures your executable file, you want to make sure that they can't actually analyze it like we've been doing. So that could be preventing them from doing dynamic analysis, like if they upload a file to a platform like any.run, which we talked about briefly at the end of yesterday. It can detect, is it running in a virtual machine? Does it only have one processor core? Does it have a VMware network interface card? Things like that that are going to give away, this is probably not a real user's machine. So that can be part of it, is just preventing that dynamic analysis. The other part of it too is we can prevent the static analysis like we've been doing for the last couple of days. So when we open up a program in like GDB, we're stepping through those instructions, we can detect that and prevent that program from actually doing its malicious things. So depending on what like the malware's intent is in anti-debugging, it can simply close the program, do something harmless and make it look like it's just a fine, okay executable, whatever nefarious things they want to do with your machine at that point. So how can we detect if somebody is analyzing or watching a program? So I give a few examples of things like the VMware network interface card, single processor core. Have you heard of other techniques or things we can check to see if someone's watching?
I was reversing a malware once that went through and checked the names at the top of all the active Windows panes in the Explorer and looked for common names like anti-debug and IDA and stuff like that.
That's a good one, yeah. We can scan all of those image names that live in memory and see if tools that are very clearly analysis tools are running. What else?
There's a virtual machine flag somewhere that would be flag.
Windows has a IsDebuggerPresent call.
Yeah, there's like data structures that live in memory that tell Windows if a debugger is attached to a certain process or not. And the reason for that is if we're actually debugging a application for legitimate purposes, if that application throws an error, we need to handle it differently than if a user was encountering that same error. So there's some kind of interesting things that we can do with Windows to check this stuff. We're going to look at a couple of different ones using Windows API calls. So just built-in Windows functionality to check for those flags and things like that. We can write our own checks to manually check those data structures that live in memory. We can do some other stuff like checking how fast an application runs. Right, so if an application's running in a debugger, we can assume that's going to be much slower than if it was just executing normally. So we can add in some like timing checks and things like that. We won't go through all of the examples I have in the slides today. We'll kind of just pick 3 of the more common or I think interesting ones. But just be aware there's like a little bit more out there for you if this is kind of a topic you like. So to check those flags that live in some of those data structures, we need to talk about processes and threads when we run an application. The way I like to think about it is when you double click an exe, that launches a process. So that is like the application or the thing that's running. The threads in that process are what can allocate those resources, execute the instructions. They can divide and conquer and kind of speed up that application as well. So to keep track of those processes and threads, Windows has 2 different data structures that are attached to every one of those running applications in memory. The first data structure that we look at is called the TED. So the TED is the thread information block or the thread environment block, depending on how old of a Windows operating system we're working with. But basically what it does is it keeps track of some of those different threads that we have running in that process. There's a lot of different stuff in here that we don't necessarily care about. When we're thinking about anti-debugging, the only reason that we use the TED is to find the process environment block. The process environment block is what can actually tell us if an application is being debugged or not. So the reason that we have to use the thread information blocks is they're a little bit more visible to us. The process environment block, which contains those flags of things being debugged or not, is called an opaque data structure. So some of the values and things in there aren't very well documented, and they're kind of blinded from the user. So this data structure lives partially between the kernel and the user space of Windows. And so we can't really see everything in there because the user shouldn't be able to access things in the kernel, but some of that data structure has to be exposed to the users, and that's where we can start to look at if something's being debugged or not. So if you actually look at the MSDN documentation for these things, they give you a little bit of insight into what those data structures look like, but for us, if we can find that PEB, the process environment block, they have a byte that's just allocated saying, is a debugger attached to this process or not? And so every time we launch an application like WinDebug or X32Debug, that flag is going to be set so that it knows how to handle any exceptions or things that we have. So it's like a very normal Windows thing that's going on. This gets really deep into the weeds of Windows internals, so we kind of take just a high level. The thread environment block helps us find this, which is the process environment block. And if we can find this data structure, we can just find that byte and figure out, is a debugger present or not? So this is a really easy anti-debugging check to implement. So if we were writing some sort of malware or things like that, we can just use the Windows libraries, and there's just a function that says, is debugger present? And it's going to return back that byte, which will be true or false. So if we import one of those Windows libraries, run this function, we can read the answer back and it says, yes, you're being debugged, or no, you're not. And then we can change how our program's going to run. So if we're trying to be malicious and we see that comes back as true, we'll hide our program or close it or do something just totally benign. And if the debugger's not present, then we can do all of the malicious things with that. So let's actually go implement that into our code. and see what that might look like. So before we get too far, we should probably actually make sure this code compiles and runs before we implement all the cool stuff. So in Windows, if you open up your Start menu, I've pinned the Visual C++ 32-bit command prompt on here. This works just like a normal command prompt, but it has the Visual Studio compiler in it. And this allows us to actually compile that binary. So much like what we did with GCC, it's just the Windows flavor for that. So if we launch the 32-bit, we're going to get a 32-bit exe. If we launch 64-bit, we'll of course get the 64-bit. So I'll open that up and then get back to my desktop. So you can browse to wherever you saved your files. So there's my path. And I'll put up the command that we used to compile this as well. So what this command does, the CL is just like what you'd run with GCC, so it's the actual program that's going to compile this. The slash, that's a capital O, not a 0. So it's capital O, lowercase d, turns off all of the compiler optimizations. And then anti-debug is just whatever I called my C program. And if it compiles successfully, you should see here that you get the executable and the object file as well. But we're mostly concerned about that executable file. So go ahead and try to run it and see if it runs okay.
Is that an O or a 0 in that compile?
It's a capital O. Yep. So let's make a new function in this program, and we can use one of the Windows APIs and just check that data structure and see is a debugger attached to this or not. So I'm going to make a function here. I'm just going to call it check1, a very original name. And for this first check, we can make a really simple if statement. And we'll call that function that exists in the Windows API. It's just IsDebuggerPresent. That's going to return back that 1 byte from that data structure. So it'll be true or false. If a debugger was present, we're going to call our caught function. And if it doesn't see a debugger present, we'll just print out a message saying everything looks okay. So I'll call check1 from the main function. And once you have that typed up, just go ahead and recompile it, run it normally, and see if it says anything interesting. Otherwise, if everything seems to run okay, we'll open it up in a debugger and see if it throws the error. I'll recompile mine. So just hit the up arrow, get the same command back. We'll just keep using that. And then if we run our program again, check1 didn't see a debugger, which we expect, right? Because we're not actually running this in any sort of debugger. So making sure it works before we go try to break it and mess with it. So in Windows, we have a couple of different options for debuggers. I like to use x32debug. It's similar to some of the Linux applications like ollie-debug. It just seems to be a friendly, kind of nice interface to use. A lot of people use WinDebug, which is a little bit more capable, but it introduces more of the command line syntax to everything you're doing. So I think for basic stuff like this, it's a little bit more complicated than it needs to be. So we're going to launch x32debug. And you can do a file open and double click on your anti-debug.c file or exe file, whichever one you called that. Okay, so now that this process has been launched in the context of a debugger, we can see in the window down here it hasn't really started executing the program. It's hit the program's entry point, which is going to do some setup for Windows, kind of laying out the memory and everything that it needs, and then it actually starts to execute the program. But as soon as we launched this process in that debugger, that PEB data structure should have set that is being debugged flag. So we don't really need to set any breakpoints or do anything special. We can just run the program and see what happens. So to run the program, up in the top right here, or top left, you should have the run button, it's just a little right arrow. And you might have to click it twice. Mine closed out.
Oh, the window disappeared?
Yep, and the reason for that, I didn't think about this. Because if it catches a debugger, it's not going to pause and do anything. Right, if it didn't catch the debugger at the bottom, we had that scanf to like sort of pause the program. So let's actually just copy that and we'll put it up in the caught function. There. Does anyone know of a better way to pause a C program? Just sleep for arbitrary number of seconds. What was it? Infinite while loop.
Percent star D, which would just throw away whatever it scans in, and then no variables.
Like that?
Yeah, I'm gonna get rid of in B.
Okay. This is a fine example of testing in production. Go ahead and reopen that binary file up in x32debug again. We'll see if it works this time. Okay, so now when you hit the run button a couple times, we can see it enters into that caught function, and then it says no debugging allowed. This is where it exited out last time, but it didn't see anything. If you type in any number, hit enter, it's going to close that program out. And there it closes.
So in this case, if you were trying to investigate a piece of malware, they've taken away the debugging ability. There's no way to put that back, but you still can look at the reversed code.
That's a really good question. So if you think about like this logic here, it's just an if statement saying if this returns back true or false, we're going to be catching the debugger or not. It's really similar to what Andrew showed everyone with the checking our product key. So we saw how we can patch that binary to say even if we have the wrong product key, just continue on. We use that same type of technique to bypass this.
So if you decompiled it and it's in Ghidra, you would see that immediately.
Yep. Yeah, so in Ghidra, if you have like the symbols loaded, you can just search for IsDebuggerPresent, and you can find that function call pretty easily. So that's one of the reasons that this isn't the best way malware authors can check for debugging things, because it's pretty easy to detect and pretty easy to defeat that check as well.
When you're debugging that, can you change that flag?
We can. Do you guys want to try that? Yeah, let's do that in our debugger actually. So since that program closed, because I typed in the number, hit enter, it closed the program, we have to reopen that process here. So I'm going to just reopen our anti-debug.exe and let it pause here wherever it's at. And we need to find our different functions that we have in this program so we can set a breakpoint, see where that flag is being checked at, and then flip it so it says we're not actually being debugged. So a couple of different approaches we could take is we can open this up in Ghidra, analyze it, look for all those functions, find the memory address and set a breakpoint there. Or we can try to do it all in x32debug. So to find where we need set breakpoints in x32debug, I'm first going to check the symbols tab. So in the symbols tab, depending on how you compiled that, when you click on the different executables and DLLs, you can sometimes find the actual function names that we've written. So you'd see things like main, caught, check1, that kind of stuff. Now I don't know if we gave it the compiler options that we needed to get those symbols, but we should still be able to find out where that function is. So I'm just actually going to double click on anti-debug.exe, and it's going to bring you right to the start of that function. When we're here, we can do a F2 on the keyboard, and you'll see that turns that memory address red, and that'll set a breakpoint when we get to that part. So what function does this look like? If you look at like the comments or the strings on the right hand side, what function does this look like? Looks like our caught function. So this is not the main. We want to find out where main actually is. So one way that's not an exact science is I just kind of scroll down, and you can usually see the different functions. There's better ways that we can find the actual addresses in Ghidra, but this works for us pretty well. So what function does this look like? This looks like check one, right? So this is probably where we actually want to set a breakpoint at. So right at the top of check one, we can walk through what's happening in this function. So first thing that we have is our push EBP and our move ESP into EBP. What part of our function was that? It's prologue, right? The next line down, we have a call to IsDebuggerPresent. And that's not a function that we wrote. It's not something that we probably want to debug. It's just part of the standard Windows API. So let's maybe set a breakpoint down here where we have that test EAX. So I'm going to do an F2 there, and you can see that memory address turns red again. And if we can pause our program execution when it hits this part, we should be able to flip that test around and show that it's not being debugged. So it's kind of like that live patching Andrew did in GDB. So when you have that breakpoint set, you can go ahead and run it or continue on. So I'm going to keep clicking run until I hit the breakpoint. And you'll know that you hit that breakpoint because the text colors invert, so you have the red text with the black background. And we're sitting right here at the test EAX. So we're trying to determine, does EAX equal 1 at this part? And if so, we're going to jump or not jump. So what could we do to make sure that this test fails and that the jump gets taken? You see down here in that middle pane, it says our jump is not going to be taken. We want that jump to be taken. Have any ideas on what we could change? What are we going to change EAX to? Change it to 0, right? So if you just click on EAX, or double click it rather, you can set EAX to whatever value you want there. So instead of setting it at 1, let's just change that to 0 and hit OK. And if we continue to run this, we'll see what happens. Although I'm not sure if that's going to work, so it says our jump is not taken still. Let's try to run it and see. So I'm going to hit run again. And there you can see it looks good, and the check one did not see debugger. It's super cool. So I'm assuming that message doesn't update until we, did you say step through? Okay, so it doesn't dynamically update like we saw in Ghidra.
Is the PEB writable? Like, would it be possible to build a debugger that immediately after attaching to the program just overwrites that flag with the 0 so that call doesn't?
Yes. So there are methods. If we know that that flag is going to be set in the PEB by all of our Windows APIs, we can also write to that and change it so it says there's no debugger present whatsoever. So we can actually defeat it at that level. Let's take a look at some of that and figure out how we can actually do this. Okay, so just to make you aware of some different API calls that can handle kind of the same thing, check remote debugger present works almost identically. This is not typically used for checking a remote system, it's for checking a remote process. So if you use check remote debugger present, but give it your current process ID, it's effectively checking itself. So that's kind of a cool one there. There's some other ones, NT-query information process. It's checking just a different data structure in memory that happens to be very similar to the TEB and the PEB. So there's a few of those in there, but let's talk about manually checking data structures. And this will kind of lead into what Andrew's question was. The problem with relying upon Windows API calls is that the analyst can do what's called hooking those API calls. It's basically like if you control those files and those calls and what they're returning back on your own system, you can have the IsDebuggerPresent call always return false. Right, so you're trusting that the analyst hasn't modified or intercepted those calls and isn't returning correct values. So that's one technique we could use as the reverse engineers to hook any of those calls, have them always say we're not debugging, and then these checks would always fail. So if we know that this data structure lives in memory, we can actually access that directly and not rely upon the Windows API. So the way this works is we're going to rely upon a standard 100% always there offset based off of the segment register. So in Windows, the segment register always points towards the current structured exception handling frame. So it's a data structure in memory. If we know where the structured exception handling frame lives, we can find the TEB. That's the standard offset, so it's going to be 18 bytes away. And if I can find the TEB, what does that tell me how to find? Yeah, the PEB, where the IsDebuggerPresent check flag is set. So if we calculate all of these offsets, and it's always going to be a standard number, we can find that data structure and actually manually check that flag ourselves. If we find that flag, we can just change it there as well. So let's find this in our current program, and then we'll actually implement a manual check as well. And then I can show you how we can change that data that Andrew is talking about. So back into X32debug, if you go to the debug menu, just hit restart, and you can hit run. And mine right now is paused at the line that says entry point. I think that should be an okay place for us to modify this at. Okay, so if we look at the listing of all this, and there's like a Wikipedia page that shows you from FS0 what all of the offsets actually map to. So you can just pull open that page, and I'll put it on our GitHub and find out what these offsets should be at. But the PEB is always going to be 30 hex bytes away from that segment register. So if I just want to see that data structure, what I can do here in X32debug is at the bottom you have a little command window. If you type in D for like dump bytes, FS for that segment register, colon, inside of square brackets do 30, and then hit enter. Dump bytes. Yep, so it should change our display window to be at this offset and then give us all the hex bytes for that. So when you run that, it moves your cursor up to here. So mine's at address 2A9000. We know that based on where that segment register is, if we're 30 bytes away from that, we're going to be at the top of the PEB. So what our job now is to do is figure out which of these bytes represents that IsDebuggerPresent flag. So I'm going to pull open that data structure here. So right now, where we just seeked to is the very top of this data structure. So how many bytes away from where I'm currently at do I need to go to find the being debugged flag? You're right, it is 3. The reason for that is this first reserved array of 2 bytes. We don't know what that's really for right now, it doesn't matter, but this is the data type of a byte, and it's an array of 2, so there's 2 bytes. The third byte should be being debugged. So we need to be 3 bytes away from where we're currently looking at. So if I look in this memory map here, we see the very top of the PEB. So here's that first reserved structure. So I've got 1 byte, 2 byte, and the 0, 1 would be our third byte. And this would represent our being debugged flag. So why not just change that? So if we right click it and go to, I think, binary edit, and just erase the 1, so it becomes 0, 0, that flag should now be set to false, so we don't have a debugger present. Hit OK, and you can see our byte that we changed turns red. And once you have that done, go ahead and execute your program and see what it says. So this is one I usually build some CTF challenges and things for my students, and I make them manually defeat all of these debugging checks. There is a plugin that you can load into X32debug that just does it automatically for you. But I'll never show the students that until they've completed it the hard way, because then they just turn it off and don't learn anything.
What did you click to change the bytes?
Yeah, so when I found this red part was 0, 1,
Yep.
I just right clicked it, went to binary,
Oh.
and then edit. And then down here in the bottom of that hex window, I just deleted the 1 and should be set.
Okay.
So if I run this again, we're going to hit our breakpoint in that check 1 function. I'm just going to run it and hope our thing works. And there you can see we've defeated the check that way. So it's pretty cool.
When you found out there was a debugging check, looking at the debugger,
Yep.
was that because is this debugger working as both a debugger and a disassembler at the same time?
In a way.
Because that same API call you had IsDebuggerPresent or something. That exact string appeared in the assembly code.
Yes.
Right? So is that just because we have the source code here, or that would happen if you IsDebuggerPresent?
That's a really good question. So you can see the name IsDebuggerPresent stands out pretty obviously. When you look at the symbols that we have, I clicked on the anti-debug exe initially, and since I didn't provide any symbols, you don't see like friendly function names or anything like that. IsDebuggerPresent actually lives within kernel32.dll.
Okay.
And so that's one of the standard imports that Windows has. So in those standard DLLs, you'll actually find all of those symbol names.
Gotcha.
So that's another reason that using the API calls directly from Windows isn't very good, because we can always resolve those.
So can you, let's say the malware author here, could they still do that check without using the Windows API call?
Yeah, let's write it.
Okay.
Yeah, we can check this manually, because if I know where the teb lives, and we know the teb helps us find the peb, and we know that's always a standard offset from a register, we can actually write inline assembly in C to check that manually for us.
Because that value of whether it's a debugger present or not is always in the same.
It's always going to be in the same spot.
Okay, gotcha.
Yep, so let's modify our C program and write that as our second check. Okay, so I'm going to close that program that opened up in X32debug. I'm going to comment out check 1, because we don't want to have to keep defeating these every single time. We'll leave it in there, but we won't actually call it. And let's make a new function here that we'll have as check number 2. So check number 2, we're going to do a little bit of inline assembly. So to make our lives a little bit easier, we're going to create a new type def at the top here. So the reason I'm doing this is that 1 byte value that comes back from the peb is going to be an 8-bit unsigned data type. So this will allow me to return that data type directly back from the peb. So that's 2 underscores for inline. We're going to use that new data type that we just created. So the uint 8t is what we're going to return from that. And we'll find check 2. So at the top of that function, I'm going to make just that 8-bit unsigned integer that's going to hold that 1 or the 0 back from the peb. And that's what we'll return back from this function. And then we can start to write our inline assembly. So the reason I'm using inline assembly here is it's easier for me to directly access that segment register and then pull back that data into EAX or one of our general purpose registers, and then we'll set R equal to the value of whatever was in that register. So our first instruction that we're going to do is we're going to move into EAX the first thing from the PEB. So that was 30 hex away. We'll then take that being debugged byte and put that into EAX. So if you remember counting at 0 is where that array is going to start, we have 0, 1, 2 would be that third byte. So why that looks a little bit different there. And we're going to move into R, AL. So I'll add some comments here. So that first line, we found the process environment block from the TEB. The second line finds within that PEB data structure the being debugged byte. That saves the byte into R. And then we can return that value back to our main function. Okay, we still need to do something with it. So we have to call this function, figure out if we're being debugged or not. So let's do something like if check2. So if that returns back a 1, we can call our caught function. Otherwise, we'll do a printf and say check2 didn't see anything. Okay, when you have that all typed up, go ahead and recompile your program. And it compiled successfully this time, which is mind-blowing because we added more weird stuff in than what we did before, but we won't ask the hard questions. And after it's compiled, go ahead and open it back up in X32debug, and we'll probably have to reset our breakpoints. Actually, when you go to the breakpoints tab, do you still see your breakpoint on test EAX? So maybe we don't have to reset those breakpoints. So if you still have those, go ahead and just run it. So there you can see our entry point. And if we run that same command that we did previously at the bottom there, you can just hit the up arrow and get your previous command back. So we have that D, FS, square bracket 30. Right there we see our is being debugged flag is back. And so our check should say we're going to debugger catch us and then close the program. So if we just keep running it, there you can see our manual check caught it. Change the flag, change your compare. What we just implemented in that inline assembly is almost identical to what the Windows API call is doing. Okay. So if you see this, everything you'd have done to defeat the API call can work here, besides hooking it. And so since there are some really common checks like that, like we just looked at the being debugged in the PEB, but some of those different API calls I showed you, like the NT query information process, those are all known and kind of standard, just like this. So the cool thing I like in X32debug, and this is what I don't show my students until after they've already done it, is if you open that file up again. Okay, so when you have that file open, if you go into the debug menu, down at the bottom you have the advanced menu, and there's just an option that says hide the debugger in the PEB. So that goes and just changes that byte for you. So if you select that and we're to just run this program, it's going to say check2 didn't see anything. There's other plugins you can download that'll patch some of the other stuff, but that's just the built-in. All right, I want to show you one more technique, and we can talk about it a little bit. We might not be able to actually implement it till after lunch because it's going to take a few minutes to write the code for it. But we can add in other anti-debugging checks that aren't going to rely upon a data structure that's always going to be where we expect it to be. Because we saw how easy it was just to enable that hide debugger from the PEB. So it's not a very reliable anti-debugging check. So a different thing that we can do is one of the ideas that we talked about previously was we can figure out how long a program should run. And if it seems like a function or that program's taking too long, we might suspect that an analyst is watching, and then we can close the program that way. And so that really doesn't rely upon anything in Windows memory like that. It's just going to be strictly how fast did that program run. So there are a couple of different ways we can accomplish that. Number one, you can use the system time. But what's the problem with relying upon the Windows clock and time down here? Like, if I'm the analyst, what can I do to make it look like it didn't take any time?
You can manipulate that.
You just change your clock, right? It's also not super precise. So the level of precision goes down to like seconds or milliseconds, which, depending on the function we're writing, might happen much, much faster than that. So that's not always the best way to do that. There is a technique using a function called RDTSC. So what RDTSC does is it keeps track of how many ticks your CPU has gone through since booting. So the faster the processor you have, or the faster the clock of that, the faster this number is going to increment. So it's kind of like the Linux epoch time. Started at 0, it's just been counting up by a second for the last how many years? January 1st, 1970, right? This is kind of like the same style of timing, it's just relying upon your processor checks. So what we can actually do is write some more inline assembly and check this timestamp at the start of a function. It's going to be a 64-bit number because it's that level of precision, it gets to be that large. Do our function and then check the timestamp after the function's done executing. And if it executes fast enough, whatever we've determined is acceptable, we'll say that it's not being debugged. If it took too long, then we'll throw that debug bug flag that way. So where we left off before lunch is we were just writing one last anti-debugging check. And this check was basically going to time how long a function ran for. And if it ran for too long, according to us, we'd say it was being run in a debugger. So I pulled up the Microsoft docs on the function that we're going to use. It's called RDTSC. And just as a refresher, this is not like a time based off of a clock. It's based off of how many ticks your processor is going through. So I pulled it up just so we could look at the data types that we're working with. It's going to return back 64-bit integers, which is a little bit weird because we're in a 32-bit program. So we'll have to do some combination of things that way. But they give you a little bit of an implementation example, and then down at the bottom here you can kind of see what that data is going to look like that's returning back. So the first thing that we're going to do is try to implement this and just figure out how long does our function take to run. And once we know kind of a baseline of how long that should be, we can set the threshold of where we start to think somebody's maybe debugging it. So if we open up our program again, we made it through check 2. And just so we don't have to keep defeating those anti-debug checks, I'm going to comment out all of our calls to check 2. Then we'll implement our third and last function here, and we'll call this one any creative names.
Check 3.
Check 3, I like it. Okay, so a new function called check 3. To handle those 64-bit numbers, because we've been compiling this in a 32-bit program, we have to define a couple of variables a bit differently than what we've done in the past. So we're going to create some ularg integers. We'll call them start and end. So kind of the flow of this is we're going to start a timer so we can keep track of what our initial value was. We would do something interesting, so this could be like the malicious part of your malware or whatever it may be that you're trying to time. And at the very bottom, we'll stop the timer and then just print out the message of how long it took to run. So it'll be interesting to see, since I'm running on a local virtual machine and most of you are all running in the IA lab, how different our processor times are going to be. So it's kind of one thing we have to think about when we're doing this type of anti-debug check is what type of system is it going to be run on. If it's a little bit slower, it's not going to have as many of those processor ticks. So we kind of have to do a little bit of guesswork on that, but since we can control the machine, we can see how long it's going to take exactly on ours. So we'll do a little bit more inline assembly, just like what we did in check 2. So we'll set up that first block of code. And this is where we're going to start our initial check here.
Just a quick question.
Yeah.
Is it possible to figure out the frequency of the CPU and then you can translate that to the time?
I suppose if you knew the speed of the CPU, you could probably guesstimate, but yeah, if it's
Frequency fluctuates.
yeah.
So, okay, so the frequency to tick is not...
No, it won't translate probably really easily. You'll see how fast these functions run and stuff though, and even if you double it, it's still going to be fractions of a second, so it's pretty easy to pick a threshold that you know is not acceptable. Alright, so in my first block of assembly code here, I'm doing an XOR of ECX and ECX. What does that actually do? Alright, so we want to have nothing in ECX, we're going to start adding back to that register there. We can then call RDTSC. And this is the little bit weird part, since we're doing a 64-bit number in 32-bit variables, is into the bottom half of start. I'm going to move EAX into the low part of that. So we take that 64-bit number, chop it in half. We're going to take the lower 32 bits and move those into EAX. Or excuse me, move what was in EAX into that start variable. And into the high part of that variable, we'll move whatever was in EDX. So to handle that 64-bit number, RDTSC just splits those 64 bits across EAX and EDX, and then we combine them together into that single start variable like we have here. Let's just make a loop. This will be interesting. Well, maybe it's not that interesting, but it'll be something we can watch. Let's have our machines count from 0 to, I don't know, 999,999,991. How long do you think it's going to take your computer to do that? 30 seconds? I have no idea. We'll find out together. So to save ourselves a little bit of typing, go ahead and grab that entire block of inline assembly that you just wrote and paste that down below your for loop that's counting up to the super high number. And then what we need to do is change it from start to end. So in both those lines there, we'll have end.lowPart and end.highPart. So for us, we're trying to figure out how long did this function actually take. So we have to figure out how to print this out. I'm gonna say, I think if we do %LLU for our format specifier, that should be able to print out that unsigned 64-bit number. We'll see. So what I want to do is actually do the math of, if we take the end part and subtract the start, we should figure out the time span that was in between those two things. So I'm going to combine the n.lowPart and n.highPart together, so it's one 64-bit number. So we'll do a end.quadPart minus start.quadPart, and we'll see if this works. Yeah, good catch. Yep, so it should be capital Q, capital P. Yeah, that's how that function's defined.
Okay.
So when RDTSC runs in a 32-bit environment, it knows to split that value across the two registers.
And does it always need to run inside the assembly?
You can run it outside of the assembly. If you look at the Microsoft docs, they give an example of what that would look like there. Yeah, and this is in C++, so I'm not sure if in C, if we can do that directly too. But. Oh, so I had ularge integers. Should just be integer. So that fixed a lot of the errors. I'm still having an error somewhere in here. Try that. Interesting. Okay. So the fix we did, so there's two things that were wrong with my program I had. I had ularge integers with an S, so just take that S off to make it singular. And then I had integer I defined in the for loop, move that out to the top of the function, and then it can just be I equals 0 in the first part of the for loop. So if we compile it, hopefully we don't get any errors. And when you run that program, it should count out to our 999 million. And we forgot one very important thing. Calling the function. That was the first test of today. You guys passed. Okay. So if we actually call the function, it'll be a little bit more interesting. You can recompile it. And then run that function. I'm starting to regret the number we chose.
You should try 90,000.
Yep. So go ahead and stop this program if it's running. Just Control C. And let's adjust this a little bit. We'll say to 9,999. Okay, so you can recompile it, run it again, and down at the very bottom, right, once it hits that 900 or 9,998, it'll tell us how many processor ticks that took, which is a pretty large number, right? But it kind of demonstrates how fast your processor's running to that clock speed of it. So you're all at 3.7 billion. Here's where you get to make fun of my MacBook because it was slower. So mine's like 4 billion. So let's say if our clock ticks were more than 5 billion, would we say that's a reasonable amount of time for your computer to execute this code? Probably, right? So we can add in some logic for this. And we could do something simple like if end.quadpart minus start.quadpart is greater than 5 billion. Then we'll say our function has been caught in a debugger. Else we can just do our printf statement. Okay, go ahead and recompile that one more time. Run it again and just make sure that you're getting roughly the same number, or like it's at least passing your check. So one last time, we're going to open this up in x32debug. We'll set a breakpoint on that for loop, or right after it, something like that, and then basically to show that if this takes too long, we'll flag that as being debugged. So I'll open up anti-debug.exe again, and we need to find our check3 function. So to do that, I'm going to go back to the symbols table. And if you double click on your anti-debug.exe, it's going to bring you to the top of the function structure that we have in here. And if you scroll down a little bit, you'll see the different checks that we've had. So we have check 1 there. Below that looks like check 2. So let me set a breakpoint within check 2. Where do you all think would be a good place to pause this? It has to be somewhere in between our start timer and our end timer. And we don't want a breakpoint in that for loop. Why don't we want a breakpoint there? It's going to hit it 9,999 times, which is not a good use of our time here. We'd want to do it probably after the start time, because if we set the breakpoint before the start time, we won't have started that clock yet, so it'll still just execute normally. I'm going to put one actually right here in this line, right above that second RDTSC. So at this point, we've already started the start timer. We've let the for loop go its 9,999 times, and now we're setting up to stop the timer. So I'll set a breakpoint here on this line. Mine happens to be 401 0A5. Yours might be slightly different, but wherever it is, right above that call to RDDSC. Okay, when you have that breakpoint set, go ahead and just run the program. I still have my other breakpoint set from before lunch, so we'll have to jump through a couple of them, but not a big deal. Just keep hitting run until you see that new breakpoint you set. So there I've landed on that XOR of ECX against ECX. And so my start timer's already been started. I haven't stopped the end timer yet. So theoretically, there should be too many processor ticks when we get out of this function. If I run it past that breakpoint and check our program, see what it says here. It's just paused at 9,998. And if we keep going, because we're at the top of that no debugging function, then it should give us our message saying no debugging allowed. Cool. Kind of just an interesting way to look at different methods of doing some anti-debugging. So of course, the more layers of the stuff that you would add in makes it more and more difficult for the analyst's job. Even if you start to combine those anti-debug checks. Right, like within our timing check, we could call check 2 again. So it'd have to continually defeat those types of things. But that's what I got for you on Windows anti-debugging. I think Andrew's got some stuff on Linux. A little bit different world on how that works. So turn it over to him.